Okay, so next in exercise 3D, I'll move on to question 9. So this is a little bit different from the previous part. So previous part, first we discussed about springs, then we discussed about strings, and now we are going to discuss about two strings and two springs. So we are going to have questions involving two springs or two strings. Okay. Okay, let's see how it's done. A particle P of mass 0.4 kilogram is attached to two identical light elastic springs, each of natural length 1.2 meter and modulus of elasticity 12 Newton. What's happening? So you have a particle like this over here, and this particle is attached to two light elastic strings. Can you see? Light elastic springs. They are identical. Natural length is the same, and lambda value, so natural length is 1.2. And lambda is 12. Lambda value is 12 newtons. They say the free ends of the strings. Can you see the free ends of the strings? The springs. Okay, they have used strings and springs, both the words here. Okay, so I'll just draw straight lines. Are you okay with it? We really don't need to draw all these curved lines. We'll draw straight lines. It's easy, even if it is strings or springs. Okay, so then the natural length is 1.2. The free ends of the strings are attached to points A and B, which are 4 meters apart. Guys, can you see what's happening here? What are they doing here? They take this, now this is at its natural length, 1.2 meter each, attached to the particle. And what are they taking the free ends? They're taking the free ends and they're stretching it. Can you see? You're stretching it to both to either side, and you're attaching it to points called A and B, which are 4 meters apart. Do you get what's going on here? Yeah? Can you understand what's going on here? So basically, you're going to stretch this particle. So what happens even if you stretch? Do you think the particle will it move towards one side, or will it be exactly in the middle? So when you stretch from both the sides, it will still like be exactly in the middle, right? Okay, so you have the stretching happening here to both the sides. Can you see? Mhm. Can you see? So these are the points A and B. These are the points A and B. Okay, A and B, which are 4 meters apart. So if A and B are 4 meters apart, how much will be the length over here on each part? Each part will be 2 meters in length. Do you agree? Each part over here will be 2 meters in length. Are you following me? Okay, and then what are they doing? So you understand when you pull it, so the natural length will be 1.2, the natural length. We mark it towards the ends A and B. Can you see the natural length of each string? Can you see what's going on? The natural length of the string was 1.2 meters. So natural length, can you see I'm marking it towards the ends A and B because the two strings were pulled, right? So the natural length, you will mark it towards A and B because, you know, if the particle would want to come always towards the natural length. So it's being pulled on either side. That's why it stays in the middle. Okay, so you mark the natural length towards the ends A and B. How much is the extension currently? How much is the extension? If this is 2 meters, you can see lateral length is 1.2. Each string has been extended a distance of 0.2 meters. Guys, are you with me? Each string has extended a length of 0.2 meters. Each string is extended to a length of 0.2 meters. Are you with me? Okay. So this is how the particle will be in equilibrium. Are you with me? So the particle would be exactly in the middle. Each string has stretched a length of 1.2 to 2 is 0.8, right? So the extension, each string has extended length of 0.8 meters and the particle would stay exactly in the middle. So do you agree that this is the equilibrium position? This is where the particle would be at rest. Are you with me? Okay. So now we come to the place where we start the simple harmonic motion. They say the point C, now look at this very carefully. The point C lies between capital A and capital B such that AC is 1.4 meters. What do you mean? Where is the point C? AC is 1.4 means what? You can see A to this natural length is 1.2. AC is 1.4 means before the center, right? So somewhere over here, shall I mark the point C? Where shall I mark the point? See, AC is 1.4 meters. Can you see? AC is 1.4 meters. And what are they saying about this point C? Why is point C so special? AC is 1.4 meters. C to B is 2.6. Do you agree CB is 2.6? How does it become 2.6? This itself, half of the length is 2 meters. I think you can see this small part is zero point 0.6 meters. Do you see it's 0.6 meters? Why is it zero point 0.6 meters? This is 2 meters, and if this is 1.4, you need to realize the remaining length is 0.6, right? 0.6 plus the 2 meter is 2.6 meters. Can you see? So it's correct, right? AC is 1.4, C to B is 2.6. Agreed? The particle is held at C. Oh, so what are we doing here? The particle, now you know the particle is in equilibrium over here, right? But what are they doing? They are taking the particle to the point C and they are releasing it from rest. Guys, so once again, it's really important that you understand what's going on here. What's going on here? The particle is pulled to point C. So if you're pulling it to point C, how much are you displacing it from its equilibrium position? Remember, the equilibrium position is always going to be the place where the particle likes to stay. Now, the particle in this case wants to stay in the middle. Do you agree? So this is the center of your SHM. And how much, and if you're pulling the particle from the center to point C, how much are you displacing? What was this length? This length was 0 0.6, right? So 0 0.6, the length that you are displacing from the center will become the amount that you are displacing from the equilibrium position that you initially move and you're releasing, that becomes the amplitude. It becomes the amplitude, the amount that you are pulling from the equilibrium position, you're pulling a certain distance amount. So that becomes that initial amount that you pull becomes the amplitude. So amplitude is how much? Amplitude is 0 0.6 meters. So amplitude is 0 0.6 meters. Are you with me? So it will go to both the sides. Amplitude is 0 0.6 meters. Are you with me? So the simple harmonic motion will happen in between these two. Do you agree? Okay, are you with me? So amplitude is 0 point because this is the place where you release the particle. Okay, so I will erase the particle here. And draw it like this. So this is the center of the SHM. Okay, so the particle you are releasing it from point C and then it will move in SHM around the center. Are you with me? Okay, so then they say, show that P moves in simple harmonic motion. How do you prove the object moves in simple harmonic motion? You have to consider the particle at a general point. So normally I'll consider the particle over here. Can you see? Not at the amplitude, not at the center. Consider the particle somewhere in between. So the x length is measured from the center. Can you see? Always you measure x from the center. So the amount it has displaced from the center of the SHM is x. Because this is a general point. We do not know the x value. Is that okay? All right. So now what we need to do here is let's mark all the forces at the general point. What are the forces we have? Do we have to deal with only one force now? Yeah, what are I'm only interested in the horizontal forces. So what are the forces we have? We have the two tensions, right? So one, we have tension towards there's tension from string A, and there is a tension from string B because you have strings on both ends. Both ends of the strings are pulling. So tension towards string A and tension towards string B. Do you agree? Okay, let's try the tensions first. PA, tension. Tension is lambda x over L. So lambda value is given to us. Lambda was 12 newtons. Okay, the most important thing here is the extension. Guys, what's the extension? What is the extension of string A? Go through this really, really carefully and really slowly. What is the extension of string A? This is the most tricky part. And if this part is, if you can understand this, then this part is done. The most important thing here is to write the extension of string A and string B. So what is extension? Remind yourself again. Extension is the length the particle has stretched beyond its natural length. The amount the string has stretched beyond the natural length. Now you can see this is the natural length 1.2. How much is it stretching beyond the natural length? You can see this part I'm coloring. This is the stretched amount, right? Can you see? This part that I colored right now. This is the length of the string that has stretched. Do you agree? Because this is the natural length. Okay, so extension is the amount it stretches beyond its natural length. So how much is this? Can you see this part of the extension? We know you can't say 2 plus x because 2 involves the natural length also. You have to only consider this colored part. Can you see only the colored part? So how much is it? You can see that this length is 0.8 plus this small length is x. The extension is 0.8 plus x. 0.8 plus x is the extension. That's really, really important. Okay, so in within bracket 0.8 plus x divided by natural length is 1.2. Are you with me? That's tension A. Can we also calculate tension B? Lambda x over L, lambda is lambda is 12. How much is the extension of string B? How much is the extension of string B? Now again, the extension is the amount. Extension is the amount that the string is stretched beyond its natural length. So once again, when it comes to string B, okay, so what is the length? It has stretched beyond the natural length. So string B, the natural length ends from here. So the length it has stretched beyond its natural length is this part, right? The part I colored in blue now. Can you see? How much is it? How much is this length? Guys, how much is this extension? Think about it. So this length is going to be, as you can see, it's 0.8 and you should subtract x. That is the extension, right? 0.8 minus x. Okay, so that's going to be 0.8 minus x divided by natural length is 1.2. Do you agree? Okay, so now let's go apply F equal MA away from the center. So when you apply F equal MA away from the center, what do we get here? Away from the center, you have tension B away, right? Minus tension A equals mass into acceleration. Mass is 0.4, acceleration is x double dot. So you have to get the characteristic simple harmonic motion equation now. Let's input the tension A, tension B is found, right? Tension B was 12 times 0.8 minus x over 1.2 minus tension is 12 times 0.8 plus 6 over 1.2 equals 0.4 into x double dot. Do you agree? Okay, so how much is the simplification? 12 divided by 1.2 is 12 divided, we can cut this out. 12 divided by 1.2 is 10. So that's 10 times 0.8 minus x minus 12 divided by 1.2 is again 10 times 0.8 plus x equals 0.4 into x double dot. So 10 into 0.8 is 8 minus 10x. 10 into 0.8 is 8 minus 10x equals 0.4 into x double dot. Are you with me? So I think you can see the plus 8 minus 8 completely cancels out. Minus 10x is minus 20x equals 0.4 x double dot. So x double dot equals minus 20x divided by 0.4. How much is 20 divided by 0.4? 50 minus 50x. So you can see I have produced the characteristic SHM equation. So therefore, when you get this equation, immediately you understand the particle definitely moves in simple harmonic motion. Therefore, P moves in simple harmonic motion. Okay, I think in this particular sum, one of the most difficult things the challenging things would be the diagram, understanding the extension. It's the diagram that is that you require to understand very well here. Okay, and then they're asking in the next part, calculate the maximum value of kinetic energy. Obviously, what's the maximum value of kinetic energy? Maximum kinetic energy is the maximum. You have to get the maximum speed. Maximum speed occurs at the center. So how do you get the maximum speed? We can apply v square equal omega square a square minus x square for the simple harmonic motion. So v square equal, what was our omega square value? X double dot equal minus omega square x. Omega square is 50. So omega square is 50 into a square. Amplitude is 0.6 square minus x is 0. So v square equal 50 into 0.6 square. How much is it? 50 into 0. Amplitude is 0.6, right? 50 into 0.6 square, that's 18. So v square is actually 18. You know what? We don't need to get the root. Why? We are trying to find not the speed, not the Vmax, but we have to find the maximum kinetic energy. So maximum kinetic energy half m Vmax square. So half into mass was, what was our mass? 0.4 into 18. V square is 18. So half into 0.4 into 18 is how much? 3.6. 3.6 joules. The maximum kinetic energy is 3.6 joules. Okay.